Okay, let's get started. So this is another day and another stream, and today um, I'm going to be talking about, or rather, I want to spend some time delving into um, this concept called automatic kernel fusion. Obviously, this thing has to do with GPUs and stuff, but very specifically, I'm going to focus on uh, a framework that's written in Rust called Burn. It's basically, PyTorch and TensorFlow and all of that stuff that you've already seen in the Python world. Can we have something equivalent in the Rust world? But because it's going to be Rust, there's a lot more as well attached to it. For example, one of the key things that you'd find in Burn is that it they also built what's called a compute language extension. Basically, it's the ability to write GPU kernels directly in Rust is possible. And I think I made a sort of a video about that as well. It's called CubeCL. So let me just bring that back and remember where that was. Yeah. So this particular project, I made a video about this a while back because basically I wanted to. It was so exciting that I didn't want to sort of lose track of that. So uh, basically, the idea is very simple. Now, I think when I made the video, there was only just Web GPU and CUDA. Now there's a lot more, basically GPU APIs that are supported. In other words, in a nutshell, if I was to describe this, so you write your kernels in pure Rust, just like this. And what happens after that is this stuff will need to be translated into, one of the target languages. For example, Web GPU uses its own GPU programming language, is what I would call it, generally called a shading language, but um, that's called Web GPU shading language. Then CUDA has CUDA itself. So CUDA is not what I think we discussed this. CUDA is not like a you have host code and then you've got uh, device code that's written separately, etc. CUDA is a unified parallel programming platform where your host code and your device code is sort of written in a single source manner. Same thing I think is for ROCm as well. Not sure. Metal is again uses metal shading language, and then you've got Vulkan, which again uses. I think Vulkan mostly uses GLSL, but they've now trying to pivot to what's called SpearV, and I've done an entire stream about that as well. But effectively, these three backends are supported only by WebGPU, right? In other words, um, so WebGPU is like a layer that's written on top of Vulkan, Metal, and all of the platform native APIs. You see DirectX 12s, you take Vulkan, you take Metal from macOS, etc. And then on top of that, you want, you basically want people to be able to access that GPU through the browser itself. So Web GPU, the standard came into being. It's not reinventing anything. It's just making it a lot more standardized and portable, so that when you write your applications that run on the GPU, be it compute or graphics, they'll just work across platforms. And I think that's the big driving factor behind WGPU, sorry, Web GPU. WGPU is the implementation in Rust. Um, so CubeCL pretty much supports all the major platforms because you might be wondering where are things like Qualcomm's Adreno and stuff like that. Not important, but I think it shouldn't be too difficult once you get once you get these things supported to move into a little more exotic space where you've got embedded GPUs and stuff. But yeah, Effectively speaking, uh, the authors of Burn also uh, have written the CubeCL project. And the idea is basically this. You do not want to have the cognitive load of trying to figure out, okay, which GPU API am I targeting? Okay, it's going to be in Metal. So I'll probably use WebGPU. In that case, I just have to write it in Wixel, which is Web GPU shading language. Then I move to CUDA. That is, I'm running on an NVIDIA GPU and I want to use the best ones. Then I'll have to sort of figure out how to get CUDA working, HIP working, etc. You don't want to do all of that. You just write stuff in Rust, which is the same piece of code that runs on the host, which is the CPU. And then you pretty much write your GPU kernels as well in Rust. Not Rust doesn't run on the GPU in the sense. Actually, no source code actually runs on the GPU. Uh, Pretty much what you can do is you can take your Rust code that you've written and translate that into the native GPU programming languages for the particular on the particular platform you're running and get your things done. And if anyone's interested, I've sorry. Uh, oh wait, I don't have it here. So I've pretty much got a video on that. Yeah. I don't remember when was that. Yeah. Um, it was a while back. Yeah. Yeah. See. So I made a three-part. See. Okay. Going to the wrong place, dude. Yeah, that's much better. So I made a three-part series of this. Um, it was very, very interesting, uh, which is why I made
Okay.
that. Sorry, stop all of that. So you can go ahead and watch it. I'll anyway link that in the description as well, in case you're interested. So just stop that and come back out. Where was I? Oh. So yeah. Uh, so basically, Burn is the framework. I haven't shown you that. Just let me talk about that. Yeah. So this is Burn. The I don't know what to call this. Okay. Anyway, let's just read it out of here. It's the next generation deep learning framework that doesn't compromise on flexibility, efficiency, and portability. And the portability part you should have got by now. That's exactly what they've been gunning for. Being able to target pretty much any platform and you're not compromising on performance because if you, like, for example, some frameworks may be, okay, we can run on this platform, so it will just run on the CPU, right? That's an option. But I think Burn's idea is, look, we we definitely want to leverage the strengths of Rust to build out an entire ecosystem for deep learning directly in Rust itself. And there are very good reasons. I've been looking at their repo and I see why it's actually very, very, it's a very good idea. At least I can say that. Um, I'll get to that part, but this is what Burn is. And they've got cool logos and stuff. Uh, I'm pretty okay. Wait, I don't see this. This is SVG. This is vector graphics, I think, because it's still perfect, man. Anyway, so you can obviously go to their GitHub repo and you can see things like the first thing that you would see is automatic kernel fusion, asynchronous execution, thread safe building blocks. All of this stuff is what you get out of the box when you work with Burn. Um, so if you're wondering, okay, is this as mature as PyTorch, etc., it's actually there in many ways, right? It's actually already there. And there's a lot of stuff that they've sort of baked into this. There's a lot of work that's gone into this. I've, just me reading the repo, I see the kind of work that went into this. So that's great. what I basically wanted to do was what I was very interested in is building off of the CubeCL work that they've done. I wanted to understand how does Burn leverage that CubeCL project to do something like automatic kernel fusion. So you don't need CubeCL to do their automatic kernel fusion, but I imagine they will want to incorporate that heavily into every part of their repo. So even before CubeCL, they were doing automatic kernel fusion. What they did is to say, okay, I can't keep writing all these kernels in these different languages and then work out. There's a lot of cognitive load and there's a huge number of pieces that I'm moving. So bring CubeCL into the picture, and then and still continue to support automatic kernel fusion. So I was very interested in automatic kernel fusion as to how does it work in Burn, and I sort of started, let's see how hard can it be. Let me just read the repo, and that was a mistake. But anyway, it was just actually fun. Um, so that's kind of what I want to talk about today, which is automatic kernel fusion and how it specifically works in Burn. Now, I don't think I'll be able to get through all of these pieces that I've mentioned over here. These are all my notes of when I've been reading through the repo, etc. Um, I think at least we get a fair bit of an idea. Let's just get into it. So the first thing is, uh, let's look at how, because we're talking about deep learning frameworks and you're talking about basically AI, machine learning, all that stuff. And the fundamental you can say type, data structure, whatever you want, entity unit that you're going to work with is the tensor, right? So in Burn, the way the tensor is actually defined is with something like this. So I've sort of made some notes. So you could write something like, okay, this is the tensor abstraction. You can see it's generic over B. There's a const generic, which is D, and there's also a K. Not important, but if I was to simply just write, um, let me actually show you something very simple. Sorry. I hope this is simple enough. All right, let me remove all this extra stuff because I was doing some experiments and things. I'll leave that. Maybe useful. Okay. So just so that you know you don't have to deal with any confusing pieces. Let me leave all of this in here. So I'm going to create a tensor from just this piece of data, this is a two-dimensional tensor with 2, 3, and 4, 5 as the elements. And then I've already mentioned that this tensor needs to be placed on a device. And I'm going to do three things. One is, all right, I just want all of this to go away. Okay, so we don't need all that. I just need one of the simplest things to do is just go ahead and play around with how these things work, and then see what output you get and start analyzing stuff. It's kind of what I've done. So you create a tensor and the simplest way to do that is using this API, which is from data. This is an explicit API. You're saying from this piece of data, give me a tensor and place it on a device. The device over here is what's called a WGPU device. And you should know if you're just looking at the syntax, you'd say that, sorry, device is a WGPU device because we specify the backend over here, and the backend is the WGPU backend. And don't need to look at the complex type signature, but that's, you're clearly calling it out, saying, I'd like you to create a tensor, and I'd like you to sort of place it here, which is using WGPU, place it on the GPU that you're working with at this point. And once that's done, you do three things. You're saying tensor clone. So you take the tensor that you just created and you say, okay, I want you to do a scalar multiplication. Then I want you to again perform a scalar addition. Not scalar addition, just an addition. And then I want to just put some random hyperbolic tangent operation on this. Okay. It's not important. It's just that you can do all these operations on your tensor. All right. And each one of these things is an operation. This is a multiplication operator. This is an addition operator. This is a tanh operator, whatever. Now, when I do print this, I will be able to see a couple of things, which is, where am I? Okay, I'm in the wrong place. So, uh, so, yeah, let's move around this. Right? You can clearly see, we're able to print the tensor. That's this particular thing. We're able to print out what we just ran through, a bunch of options. We just ran through them and we were able to see that. So that's all well and good. Um, Now, how exactly did this thing work? In the sense, you place this particular tensor on the GPU, correct? And then you performed all these three operations. Did you perform these operations one after the other in sequence? That means, did you actually send three different, let's just call them commands to the GPU? All right. I've explained, how the GPU, um, how you program the GPU, basically. There's something called a command processor that accepts commands in a command queue, and then you submit those commands as the host. You cast those commands and you submit those commands and you say, execute them. And then the GPU does its work and asynchronously reports back. We've seen all that. So just if you were to think about it, that would be stupid, right? If you were to basically say for every single operation, I'm going to have the host craft a kernel and then sort of go ahead and submit that. That's really not going to work, right? That's exactly what automatic kernel fusion is. So what we're saying is when you write code like this, you, the user, don't need to worry about how this work is going to be, you can say, submitted to the GPU, right? All three operations are actually going to be sort of fused. And then the final operation is going to be submitted. So it may look something like, I don't know, let me just try this. It may look something like let XX or whatever, and it may look like something like, I don't even know if this thing is there. Yeah, I think it's there. tanh and a tensor, and it may look something like this, right? So this entire thing that you've just written, Burn and many other machine learning frameworks will do this. They will go ahead and look at your code and say, okay, there is an opportunity for over here to sort of fuse these operations into one operation because, we can do it. And thereby, we save on a lot of things. Like we don't have to effectively launch multiple kernels. Then the memory access pattern for each one of those kernels is going to be different, etc. So a lot of the work that you'd have to put in, you no longer have to put in because you've just said, okay, this is one operation actually. Um, and I'll come to why this is very, very useful, etc. But intuitively, this should sort of tell you that this is exactly what you want. You don't want the programmer to worry about, whether or not this is the most efficient way to submit work. And that's where automatic kernel fusion comes in. And my goal is to understand how Burn does that because it's written on Rust. And it's something that I'm interested in, is all the kind of GPU work that's going on right now across the Rust ecosystem. So this is by far the most promising one that I've seen so far. All right, so let's get back to this. If you were to look at the high level overview of how tensors are defined in Burn, you should know by now that you have a backend. Uh, so a tensor is generic over B, D, and K. B is some type that will implement the backend trait. D is a const generic, and K is some type that implements the tensor kind. So when we mean what we mean by backend is that basically uh, what's the compute that you're going to use to do the work over here? Is it a CPU, a GPU? What is it? Mostly we're talking about GPU, so it's going to be a GPU. Okay, if it's a GPU, which platform are we talking about? Talking Apple, we're talking, you know, Rex X12, you're talking Vulkan, whatever. All right. And note, I'm not talking very specifically about the specific GPU. That is, whether it's an NVIDIA GPU or an AMD GPU, etc. All of them, all GPUs will end up supporting one or the other GPU APIs. And Web GPU is the API that pretty much everyone supports, right? At this point, it's a standard that everybody seems to support. So yeah, and then D over here is basically dimensionality. Um, this is a compile time constant. It's basically trying to say how many dimensions are we talking about? One, two, what is that? As you can see over here, this is a two-dimensional tensor. That's two dimensions. And then K is the element type. Is it a tensor of floats? Is it a tensor of int, bool? What is it? Now, the other thing is the backend itself can be composable in the sense that, great, you were specifically saying that you would be able to leverage the GPU I have, and you've given me a way to do that, which is okay. Um, the backend will help you out with that. But what if I want to enable more uh, capabilities? That means if I want to say, okay, while the backend will actually do the job, the real job of submitting work to the GPU, but I have these other things, like I want to do fusion, which is automatic kernel fusion, or I want to do something else fancy, whatever you see over here in their website. Uh, yeah, kernel selection maybe. All right, that's another feature that you probably want. You don't have to worry about, okay, how do I do that with this particular backend? How do I do something extra? No, you just go ahead and wrap that in another type called the fusion backend. So you take your main backend and then you wrap it in the fusion backend, and that's how you get uh, a backend that is also uh, capable of performing automatic kernel fusion. That's it. You don't have to do anything from your end. Okay. And then we've already seen this in CubeCL. This is not that important unless you want to dig into the weeds of things, but CubeCL and uh, Burn both use the client server abstraction. So for the fusion level, you got CubeCL using, sorry, you've got, so basically the Fusion backend uses a Fusion client and a Fusion server. There's examples of them, etc. CubeCL already discussed this. There's something called a compute client and a compute server. This is not very important, but yeah, it's there. So if you want to look at it, we'll anyway talk about it if that comes up. And then we have what's called, sorry, CubeCL I already talked about. So that's good. Um, and then the first thing I wanted to actually talk about was how. So I basically looked at this one line and thought, wait, there's quite a bit packed into this. You've got a backend, you've got the dimensionality, and you've got the elements. You're sort of making it generic all over all of them. That's actually pretty interesting. So how are you doing this? Well, I made the mistake of trying to find out. It's just a joke. But effectively, if you were to sum up the whole thing, is they have some custom memory management, which is, let me see if I can get, yeah. So you've already seen the generic types. I've already talked about the composability part, and I've already talked about the client server abstractions, which is not that important, but what I'm coming to was the memory management part. So how you allocate memory on the GPU, how do you effectively use it? How judicious are you with it? How are you efficient? How efficient are you with your memory usage, etc.? Counts a lot when you want to talk about performance and a whole bunch of other things, right? So in Burn, you will go through, you know, pretty much quite large, what you say, call chains before the actual work gets done. And if you're wondering why, well, that's effectively how you would be able to be portable, efficient, and performant across the board, right? So it's like to purists, this might be a scenario where why do I need this level of abstraction? Well, if you get down to it, personally having worked on projects where you had to have portability as a big criteria along with performance. Like means you really don't want to lose performance for the sake of one thing. That you don't want to make that trade-off. This becomes, I would say, inevitable in many ways. At least that's my experience. So yeah. So the first thing is just allocating a tensor and placing it in GPU memory. Talking about Not talking about GPU uh, execution at all. I'm just saying in GPUs in the GPU's memory. Now, this could be for the unified architectures like integrated GPUs or Apple Silicon, etc. It could be the RAM, or it could be the VRAM for discrete GPUs, etc. There's this flow. So you basically the memory manager will reserve some space. It depends on something. The memory manager is built around the concept of memory pools, which will do the try to request an allocation, and that will get redirected to web GPU or WGPU in Rust, and then attempts to do the main call. This is the one that actually does the work. But yeah, so that's sort of how it works. Um, and if you wanted to take a deeper look of everything that I just talked about, uh, just to give you some heads up of what that will look like if you just went ahead and say, okay, show me the entire flow. All right, so you start with tensor from data over here, and then you go through all of this, and finally at the end, you're going to be doing this, right? So there's quite a bit of abstraction involved. And that's kind of why I said there's a lot of thought that's gone into this project. And I believe rightfully so, for the kind of goals, ambitious goals that it has, right? So this is just the memory allocation that's happening over here. Yeah, so I don't think I want to like delve too much into this at this point and then confuse everybody in. So at least for the first part, I'll make this multi-part so that it's more digestible and it's more easy for me to keep track of things as well, because partly this is a reference for me. So let me just say this. So closer look is fine. We're done with this. This is the high-level overview. Basically speaking, there's a very good abstraction for the, the basic unit, which is tensor itself, and how we can work with tensors in Burn. Then, so I'll sort of end with this part, which is let's actually look at how automatic kernel fusion happens. So you remember we already sort of talked about these three operations. We said, yeah, so this is my operation. I want you to go ahead and um, basically have all these operations run on the GPU. So there's a scalar multiplication and addition over here. There's a tanh operation. By the way, Tensor allocation itself is a no-op, technically speaking. Uh, that goes to how the way the GPU APIs work. Unless you're talking about large transfers, this is not really going to be a real operation. That means anyway. That's getting too much into the GPU API. Let's just look at to get a visual understanding of how useful something like kernel fusion is. So the best way I wanted to sort of talk about this, by the way, I was doing a debug thing, so that's why this thing was like not giving me the answer and stuff. So just so that you get the answer. Yeah, I should probably remove that. So yeah, so here's what happens. This you can clearly see we are. I mean, we're not just running on the GPU and saying, yeah, it's running on the GPU. Sorry, we are not just running it on the CPU and saying it's running on the GPU. It is using the right backend with the right abstractions and stuff. All right, so let me go back here just so that I don't mess up stuff. So what was I doing? Yes. Now, there is an easy way to start off whenever we're looking at a project as big as this and as ambitious as this. There's so much stuff in there that you might get lost a bit. So just to keep us focused on the goal of understanding automatic kernel fusion in um, Rust, sorry, in Burn. Um, I basically wanted to say, okay, if I do run these three operations, can I do with and without, right? Yeah, there is a very crude way of doing things, and I'll show you what that way is. That's kind of why I have two repos over here. So the demonstration is we will force fusion, and then we'll again, you know, what do you say? Force execution as individual kernels, right? So let me show you that with these pieces, right? So just to be safe, let me just run this first. Yeah, I don't want to create stuff that is not important for this video. All right, so this should be sort of the first half. I'm just going to force fusion to actually take place. So it's going to be more than just three operations. I think I have a couple more over here, whatever. But fine. We are going to go ahead and run these code and see what actually happens. So if I did something like this, so I'm running the example that I wrote, burn test features WVB. And by the way, I just added this directly to um, the examples folder. So I made another example and I said, okay, use mine. Because using a separate project, etc., was a little bit of a headache. I noticed a couple of things. That is, we're pulling burn over here directly from crates.io, which is a little, what do you say? It's not, the cutting edge, what's on main branch right now. It's whatever we have. We could obviously use the main branch, but then again, sort of flipping back and forth between the actual code base and what's happening gets a little tricky sometimes. So just make an example directly in the burn repo itself, locally. You don't need to push it out, but and figure things out. Okay, so let me see if I can just get this thing running and look at the output. So this should come up. Um, yeah, but I did, you know, uh, clear something out. That's why it took a little longer. So when we forced fusion, this is what we got. Uh, when we didn't, when we did individual submissions as well, this is sort of what we got. The answer is the same at the end of it, but we're actually submitting three different kernels, right? And you can see that over here, where we say, okay, create a tensor, allocate one, do a scalar multiplication, do an addition, do a tanh, do another scalar multiplication, and do another addition, and then give me the final result. So the idea over here is the moment you actually go ahead and call print, that's when the work that you've actually submitted, or rather you were wanting to submit to the GPU, actually gets submitted. So the entire process itself is lazy execution. That means none of this actually executes right away. All right, you're just building up. Um, you're building up work, uh, and you're sort of queuing it up in a queue of sorts, and then you're saying, okay, when you need it, this will run. Right? We will go ahead and actually do the work, right? Printing will actually go ahead and do it, and then using it somewhere will also go ahead and trigger the same thing. Likewise, if you see over here, that's exactly how we're going to force it. We're going to print each intermediate step. So it's actually going to go ahead and do the calculation and then report back. Okay. So instead of three separate kernels, we can have one fused kernel in this option. This one over here, we can have one fused kernel, but this is three separate kernel invocations that's happening over here. Right? That's a super simplified example of things. All right. Now, with that context, let me just quickly go ahead and sort of remove the what you call the non-fused stuff and show you the remaining pieces of how this is actually happening in the back end. What's, just to give you a clear view of what's going on. So just go back to the notes. Um, so if I was to look at the generated kernel itself, uh, now I just found out that Burn itself produces a lot of logs. I'm yet to go through most of them, but you could also use Rust standard logging capabilities because Burn has a bunch of dependencies, and those dependencies produce a lot of logs. We could sort of look at that to determine exactly what happens in Burn. That means when I write this and I say, go ahead, go do the automatic kernel fusion thing. I want to see what happens. So I'm basically going to walk you through what actually happens. Uh, I'm going to run the command as well. But when you do see the command being run, you will see that the output has four different kernels that are actually kernels that basically work that's submitted to the GPU. The first one is something to do with WGPUs. The first two are, you know, because we're using WGPU as the backend on my Mac. Um, it has some setup work that it has to do, and then there's some additional stuff that needs to be, put in place. So the first two kernels that we submit are going to be buffer setup and validation. And then you will also see the fused kernel, the actual fused kernel. We'll see that, and we will see these instructions, right, in there somewhere. Saying you'd clearly be able to see that, okay, we fused everything into one single kernel, all right? This may not be very readable, etc., but that's why I made notes of here. Here's where you do the multiplication by 2, and here's where you do the addition by 1, and here's where you do the tanh operation. All of them happening in one shot in a single kernel. So we'll see that in, instead of taking up too much time, let me just go ahead and run it. All right, so I'll just remove this. This is not useless because you don't get anything from there. And I think I can actually remove, so let me just leave that there. just so that we're good. That's partly why I turned on logging, just so that you might be able to see stuff. And so pretty much everything that I need is printed. So let's just go here and see what did we get. The first thing is these two things, the debug logs. Uh, because we're actually trying to look for what's um, we're not looking at the logs that are produced by Burn or by CubeCL, etc. We're looking at its dependencies. One of its dependencies is WGPU, and specifically the metal backend. We can pretty much go ahead and look at exactly all of the capabilities that our GPU has. You can look at that. All that stuff is great. A lot of the stuff over here is graphics specific, but you'll also have other things. Anyway, for example, things like, do we support 64-bit atomics? Yes, etc., etc., etc. And then the first thing that you will see is what I mentioned. This is the first kernel that's created, and this is basically uh, the setup. So if you know a little bit of GPU programming, this is doing things like trying to check to see, okay, there's a particular limit to the kind of work that you can submit. Are you within that limit? Right? It's called dispatch limits. And it's kind of what's happening here. So that's something that needs to be done when we're using a WGPU. And then the second kernel is again sort of in the similar area over here, where um, okay, I'm not going to even talk about it. This thing has things like indirect uh, dispatches, etc., which is a little different. It's just something that you need for WGPU's initialization. That's a better way of thinking about it. Now, here is where we actually do all our printing. We're saying all of our uh, print statements over here that you see. All of this stuff is happening here. And then finally, we get to see that the actual kernel is created. And we see these are the work group sizes that we are trying to come up with, saying this is the number of threads that I want to spin up on the GPU and stuff. And then finally, uh, yep, here's where you see the main thing that you just saw, where we're doing a tanh and we're doing, a multiplication by 2. This is, don't worry too much about this. This is, um, there's a lot of, so GPU programs tend to be extraordinarily simple, all right? Uh, they're just very focused on getting the problem, getting it right, but you don't have like extraordinary concepts in GPU programming. Like, I don't even think at the end of it you will have things like generics, etc. Not really true. You do have them, but in general, they're very simple, is what I'd say. All right, then that's about it. So that's the first two kernels and the fused kernel, and then you have the slice kernel. This is basically the third one that we submit. The thing that this thing is doing is you went ahead and computed stuff, great. I want the answer back, all right? So you're going to need to go ahead and get that back. And that's kind of what the kernel, slice kernel input is doing over here, right? So you extract the data out and you format it for display because you were trying to print the tensor out. That's effectively how this thing works. That's what I mentioned over here. So when you call all three operations, these operations are recorded, but they are not executed. They're only executed when you actually, ask for it to be executed either directly or indirectly. Indirectly, something by printing. At that point, the system optimizes, that is, fuses all of them into a single kernel operation and then submits that. It's more efficient than running three separate kernels. It's efficient in terms of performance, it's efficient in terms of memory usage, it's efficient in terms of a whole bunch of other ways, right? Headache as well. Try to figure out three different kernels being submitted, what happened, etc. All right, so yeah, I wasn't expecting to take like 30 minutes for this stuff. But anyway, so that's a very, very simple look at Burn and Burn's automatic kernel fusion in action. We haven't actually looked at how fusion actually works. I'm hoping that, I was hoping that we could actually get to that part. Um, at least let me see if I can do the intuition part. So here's what we need to keep in mind when we actually want to write fused kernels, etc. We'd like to know a couple of things. Like this, in the context of fusion, you want to know, okay, so I want you to do a scalar multiplication of what? A tensor and a scalar, right? Scalar is any constant. So where do they live at this point? Are they in GPU memory? Are they still in host memory? And so the GPU itself has a hierarchy of, has a memory hierarchy. That's global memory, shared memory, registers, local, caches, whatever, etc. Um, so you need to figure out the reads and writes, which are basically memory access patterns, and you want to track them. You want to know which tensor is being read from and written from, and where is it in memory exactly. Without that information, you're not really going to be able to fuse anything, right? You really need to know that information. So you need to figure out that information from whatever's been supplied to you. Right now, all that's been supplied to you is, I'll just come to that. Where was that? Yeah, all that's been supplied to you is these three operations, right? Now you need to figure out, okay, uh, so given the users wanting to do this, I think I can figure out exactly where is tensor one being read from, where is it being written to, et cetera, et cetera, et cetera. Okay. All right. So this is why I didn't want to like get into this so quickly, but yeah, I think I can actually do this part. Uh, so forget that, but let's try that. Yeah, this is what I'm trying to say. So why do we want to do a fusion? Because you can do memory access optimization. You can do things like data dependency analysis. If you're going to perform an operation, then does that operation depend on any other operation to have happened before it? Can a bunch of operations be executed in parallel? Thereby, we can exploit that parallelism if it exists. The number one problem with GPUs is going to be trying to frame your problem in such a way that you want to find parallelism in that problem. It may not be obvious. That's the point. And then basis that, which operations can actually be fused together. And then you can also deal with things like memory usage, as I've already said, because can we reuse memory when memory needs to be allocated? All of this stuff can be figured out when we actually do. These are the benefits of automatic kernel fusion, or rather, kernel fusion itself. So let me just take a concrete example over here, and that's kind of why I have this. So what we're doing over here is we want to read we want to read tensor one because we've supplied that explicitly. This value is something that I supplied explicitly, right? So I want to go ahead and read, okay, because if I'm going to be doing any kind of compute, I at least need to read it. And we place it in GPU memory. That's usually called global memory. And then there is this constant, which is again something that where should it live? Should it live in global memory? Should it live in shared memory, etc.? The reason I'm talking about this is because that has a huge impact in terms of performance. Where data resides and how we move data to the compute uh, complex is extraordinarily important. Data movement is the single biggest bottleneck in, you know, in basically right now in parallel computing at this point. GPUs are really not bottlenecked by the compute that they have, but how much data can you move in and out as quickly as possible? That could be across GPUs, that could be within a GPU, right? So um, that's one option. Then once you perform the operation scalar multiplication, then you need to put that result somewhere, right? Where is that going to go? That's the question. Then the same thing over here, you take whatever result that you got. We're calling this temp because it's actually a temporary thing. You don't really need it, right? You just need it. You need to compute it and you need to have it somewhere for for some duration of that computation. But you don't need to have it like in global memory, which is, a more, it's not persistent, but it's it's something that you would use to sort of send results back to the host, etc. Anyway, same thing over here, scalar addition. Where is it? This is an intermediate result. It doesn't really need to be in global memory because I have to go all the way to global memory to fetch that. That's a huge cost. Another intermediate result, which is you do this, you get another intermediate result. Same thing over here. Y is red again. The final result, this Z, this thing needs to be written to global memory because that's exactly what you want. You want to see what it produced. So that part is important. The optimizer, here's the kicker. In pretty much, I guess, in every automatic kernel fusion thing, the optimizer that you build must be able to recognize the temporaries over here that you create, which is temp1 and y, which are intermediate results. They don't really need to be written to global memory. Instead, they can be in either register, the shared memory, or wherever it is that you want to put them. Only Z needs to go out to global memory. And that's kind of the infrastructure that's built in Burn with something called Fuse Block Builder, etc., where you'll see all of this. You will be able to annotate that, okay, this is a temporary, this is a local, this is a local 2, this is local 3, but at the end of the fusion piece, you should only keep Z. You should not worry about the other two. That comes from data flow analysis, etc., that actually happens on the fly for you. Now, granted, I showed you the simplest example possible, so it may not be like, well, that's not a huge deal. But imagine hundreds of thousands of operations all running concurrently in different streams of work that you're submitting. That's a lot. And that's kind of what, you know, uh, yeah, I've been focusing on. I've been trying to look at how Burn does that. So by carefully tracking these reads and writes, the Fusion Optimizer can minimize memory accesses and maximize, whatever computational efficiency you're looking for. And that basically makes all your deep learning models faster, right? So this is an important technique that's used a lot in many places. Pretty much every framework that is worth salt at this point has this. And Burn also has it. And here's how it does it. All right, so I don't want to keep this, I want to keep this video short, not too long, like hours, etc. So I hope this is what you'd say, sorry. I hope this is interesting and clear. Anyway, even if it's not interesting, it should be because I'm working on something along these lines. So yeah, let me know if you have questions or thoughts, etc. We get into the parts where Burn actually has a huge number of, not huge, has a certain, many levels of abstraction in order to get things working. The one key point that I would certainly say is, although it has this level of abstraction, I was able to actually read the code because everything is pretty much statically known. Now that's a big plus. Of course, if you go, CubeCL kernels are pretty big macros or procedural macros, and you'll need to expand them from time to time, which is something that I've already done in the CubeCL work during the CubeCL streams. So apart from that, I think pretty much everything is just static. I was able to read them without even having to debug much of it. Unlike, the struggle that I went through when I was trying to figure out how does a ROS GPU work. Okay. Um, yeah. So this is pretty exciting. I think the video that I made was many years ago. Sorry, not years ago, many months ago. Um, and this project has evolved quite a bit uh, in those 8 months. It's come a really long way. So whatever I just talked about, there's also a very nice blog post that the author, Nathaniel himself, has written. I would highly recommend you read this blog. And there's a lot of work going on. So I'd highly recommend, if you're watching this and you're interested, definitely get involved with the project. It's a project that you should really watch out for in the Rust. Not just the ML world and the deep learning. This thing can go beyond. That's at least it's an instinct that tells me that this thing has more to it, considering the way this thing is shaping up, right? Yeah. So that's kind of what I want to cover. I'll try and cover the other dense stuff, which is all very into the Vern stuff, uh, in more detail in future videos, partly so that I can keep a track of them for free online, and also if it helps someone, and if there's any conversations to be had, we can sort of have them as well. And please, if you find something that's not particularly right over here, please feel free to drop a comment, right? Okay. All right. That's about it for me. Thank you for watching. Have a good day.